Hi everyone. In this part of the lecture, we will be choosing the most stable resonance structure among a given set. Okay, so this is our learning target number 2. Decide which structure is most valid or most stable for a given set of resonance structures. Alright, so the first thing that we have to do is to assign formal charges on each atom present on that structure. And what are formal charges? This is basically the number of valence electron for that particular atom minus the quantity all of its unshared valence electrons plus half of its shared valence electrons. Now I know it sounds a little bit confusing, but don't worry, there is a shortcut for that. So let's take for example our thiocyanate ion. So this is SCN, or represented by the following resonance forms. Okay, so you see that there is nitrogen, carbon, and sulfur. Now, what we need to do is, in order to assign the formal charge for each particular atom, is to enclose it in a box. So, for example, nitrogen here, and then carbon is also enclosed in a box. Okay, so in that way we are now breaking, or we are having half, we are fulfilling the half of its shared valence electrons. Next one, so this is our shortcut. Okay, and it works most of the time now. So now that we have enclosed them in a box, the things that we need to know are the number of valence electrons for that particular atom. So for example, nitrogen here, nitrogen has 5 valence electrons. So nitrogen has 5, we subtract it with the number of electrons present in that box that we made. Alright, so in this case, this is 1, 2, then 3, 4, 5. So half of the bond, okay, we are fulfilling this, half of its shared valence electrons, so half of the bond. So we are just basically counting how many valence electrons are present in that box that we made for that atom. So this is 1, 2, 3, 4, 5. Therefore, our nitrogen atom in this case has 0 as our formal charge. Alright, now for this carbon, this is 1, 2, 3, 4. The carbon atom actually has 4 valence electrons, right? So 4 valence electrons minus 1, 2, 3, 4. 4 electrons in the box, so you get 0. And then you have sulfur. So sulfur has 6. If you try to look at the periodic table, sulfur has 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. So this is 7. So 6 minus 7 is equal to negative 1. Okay? Therefore, in our first resonance structure, we have the following formal charges: 0, 0, negative 1. Now, let's try to look at the second structure. So I leave the box making to you. And then we'll just go directly to the formal charge. So in this nitrogen, we know that nitrogen has 5 valence electrons, right? That's 5. So if there is an imaginary box here, then we have how many electrons? 1, 2, 3, 4, 5, 6. Okay, so there 6 electrons will be included. So that means this nitrogen has a formal charge of negative 1. Now how about this carbon? So imagine that this carbon has a box here, and then carbon has 4 valence electrons originally, the carbon atom, minus 1, 2, 3, 4, right? See, we'll just break the bond so that you will not be confused. Okay, in here, and then carbon. 1, 2, 3, 4. So this carbon has a formal charge of 0. Alright, and then in this sulfur, so it's broken already, we know that sulfur has 6 valence electrons minus 1, 2, 3, 4, 5, 6. So this is 0. So therefore, the set of formal charges for this structure is negative 1 for nitrogen, 0 for carbon, and then 0 for sulfur. All right. Now, how about the last structure? This is one. If you try to place it in a box, you have a unshared or half of a pair here. So nitrogen has 5 minus 1, 2, 3, 4, 5, 6, 7. So 5 minus 7 is negative 2, right? And then this carbon has, if you try to break this carbon has 4 minus 4, you have 0. And then this sulfur has 1, 2, 3, 4, 5. And originally sulfur has 6, then minus 5. So that is equal to positive 1, right? Now that you have the formal charges for each atom in the resonance structures, it is time to choose the best resonance structure. So there is a set of guidelines in choosing. So number one, the smallest set of formal charges must be present. Okay, so the smallest set. Therefore, combinations like 0, 0 or something negative or 0, 0 plus 1 are most preferred. So you have to look at the one with the smallest values of formal charges. Now, for it to be clear, let us let us write the formal charges that we found out. So, for in this structure, nitrogen, carbon, sulfur. In the first structure, that is 0, uh, 0, negative 1. And then you may not do this. I'm just doing this for clarity. Okay, this is negative 1 for the second structure, and carbon in the second resonance form is 0, and then it's 0 here. All right, and then negative 2, and then 0 and plus 1. Okay, so you might have noticed that the first and the second structure actually fulfill this first condition, which tells us to use the smallest set of formal charges. However, we need to decide which one is really the most stable. Okay, so in here it is also fulfilled this second condition, that the same non-zero formal charges on adjacent atoms are not preferred. So we do not see any negative numbers being adjacent to each other. So more or less this has been fulfilled. And then the third one is that more negative formal charge must reside on the more electronegative atom. Okay, so that makes sense because it is hungrier for electrons. The negative formal charge must always reside on the more electronegative atom. So it's a battle between nitrogen and sulfur. So which combination do you think shows us the negative formal charge at the more electronegative atom? Is it N, or is it N negative 1, or is it sulfur negative 1? Okay, so uh, which one? Maybe a few moments to look at your periodic table and try to look at which one is more electronegative. Okay, so if you look at the periodic table, the trends in electronegativity increases from left to right and bottom to top. So if you compare sulfur and nitrogen, from left to right, bottom to top, sulfur actually comes first before nitrogen. Okay, as a matter of fact, the nearer atom to fluorine is nitrogen, right? So we can say that it is also more electronegative in this part. So if you go back to your most resonance structures, in comparing, okay, in trying to fulfill the third condition, wherein it asks for the more negative formal charge must reside on the more electronegative atom, we now know that the more electronegative atom is nitrogen, right? So therefore, this combination of formal charges gives us, okay, allows us to choose the best resonance structure, which is this one. So NCS. And therefore, we consider this to be our most stable structure. All right. So another example, let's have the molecular form of NOO. Maybe we'll try to use another page. Okay, so here is our next example, the cyanate ion, which is the CNO minus, or we can rearrange it into NCO, because the least electronegative atom, carbon, uh, must be our central atom. All right. So we have the following lead structures for the cyanate ion. Now, kindly pause the video for a moment and then try to assign the formal charges for each of the atoms in the structure. Right. So for example, here in this first structure, our atom is nitrogen. All right. So we know that nitrogen has 5 valence electrons. But then if you try to imagine a box enclosing nitrogen, that is, if we divide it here, this is 1, 2, 3, 4, 5, 6, 7. So 5 minus 7, we get negative 2 for this nitrogen. Okay. And moving on, so for carbon, we know that it has 4 valence electrons, and it has 4 electrons. When enclosed in a box, you get 0. Okay. Oxygen is 6 minus 1, 2, 3, 4, 5. This is, okay, where does the 5 come from? Okay, if you just break it here, 1, 2, 3, 4, 5. So this is plus 1. Right. So in the next structures, I won't let me not break the bonds anymore, but you get the idea that you have to enclose the atoms in a box. So this is 5 minus 1, 2, 3, 4, 5, 6. So 5 minus 6, this is negative 1, right? So negative 1 for nitrogen, and for carbon, the formal charge is 4 minus 4, so you get 0. And then oxygen has 6 minus 1, 2, 3, 4, 5, 6. You get 0, right? And in this case, in nitrogen, 5, that's 5 minus 5, so you'll have 0. And then carbon has 4 minus 4. Again, the first number is the valence, the number of valence electrons for that particular atom. Okay, and then the second, the one you subtract, is the ones enclosed in an imaginary box. So this is 4 minus 4, you get 0. And then for oxygen, you'll have 6 minus 1, 2, 3, 4, 5, 6, 7, minus 7, you get negative 1. Alright? So here are your combinations. The ones in here, 2, 0 plus 1, 1, negative 1, 0, 0, or 0, 0, negative 1. So which one is your most stable, or most accepted, or most valid structure? First one is if it's at the lowest set of formal charges, and no negative charges must be adjacent to each other. And number 3, the negative formal charge must reside on the more electronegative element. So it's a battle between the second option, the middle structure, and the rightmost. Okay, so which do you think is our most stable structure? If you're saying this one, then you're correct. Okay, because the negative 1 resides on oxygen, which is more electronegative than nitrogen. Alright, negative 1 resides on oxygen, which is more electronegative than nitrogen if you try to look at in the periodic table. Alright, so later on in drawing the lead structures, we must identify or we must give the most stable or the most accurate or most contributory resonance form in case these happen. Okay, so that's it for choosing the best or most valid resonance structures among a given set. So if we try to go back to our learning targets, we have actually completed the second learning target, which is to decide which structure is most valid for a given set of resonance structures. Again, lowest set of formal charges, no non-zero formal charge, must be adjacent and negative, and the most negative formal charge must reside on the most electronegative atom. Alright, so that's it for resonance structures and formal charges. Thank you for listening.